Hello everybody, let us talk about Pauli matrices in quantum computing. Pauli matrices are named after Wolfgang Pauli, who is best known for Pauli's exclusion principle. There are three Pauli matrices of dimension 2 cross 2 which are of particular interest. Pauli matrices play a central role in spin half particles such as electrons, and these matrices are denoted by sigma 1, sigma 2 and sigma 3. And these are also denoted by sigma x, sigma y and sigma z. And these Pauli matrices will result into Pauli x gate, Pauli y gate and Pauli z gate. We will see further into the lecture. Sigma 0 is also used in conjunction with the Pauli matrices. Basically, it is a 2 cross 2 identity matrix. So Pauli matrices are building blocks for the description of any quantum system with 2D state space. So this is the sigma x or sigma 1 matrix. This is sigma 2 or sigma y matrix, and this is sigma 3 or sigma z matrix. There are certain properties of Pauli matrices. We have to look into those properties. Now, Pauli matrices are Hermitian. So these operators are Hermitian operators. Now, what is a Hermitian operator? When the matrix is equal to its adjoint. So if you take the adjoint of sigma 1, basically this is the adjoint, this is the Pauli matrix, and you are taking the adjoint. This dagger sign is actually the adjoint. What is adjoint? Adjoint is taking the complex conjugate and then transpose. So, and you will find that once you take the adjoint of the sigma 1, it will be equal to sigma 1 itself. So this is known as Hermitian property, and it will be applicable to all the three Pauli matrices. So that means all three Pauli matrices are Hermitian operators. Pauli matrices are also involutory. Involutory means that if you multiply the two matrices, it will result into an identity matrix. So sigma 1 square is basically equal to sigma 1. So what does this prove? This proves that the matrix sigma 1 is actually equal to its inverse. That is why when you multiply the two matrices, so if it is equal to its inverse, we are getting the identity matrix. So all three Pauli matrices are involutory also, and we can express in general with sigma k, where k subscript is equal to 1, 2, 3, so represents all the three Pauli matrices. So therefore the Pauli matrices are Hermitian and the Pauli matrices are involutory also. So therefore we have now proved that the Pauli matrices, with this equation we have proved that the Pauli matrices are involutory. By this sigma k equal to adjoint of sigma k, this proves that the Pauli matrices are Hermitian. So from these two equations we can say that the inverse of sigma k is equal to the adjoint of sigma k. So this results into another property which is known as the unitary property. So therefore all Pauli matrices are unitary operators also, therefore, which means that the inverse of the Pauli matrices is equal to their adjoint. So Pauli matrices are Hermitian. In quantum mechanics, the observables are represented by Hermitian operators. So all observables, because the observables are operators which can be measured. So observables are represented by Hermitian operators because the Hermitian operators have real eigenvalues, which is necessary because ultimately when we measure the property, so measurement outcomes must be real numbers. Pauli matrices are unitary operators because quantum evolution is governed by the unitary operators. So this comes from the Schrödinger equation, where the unitary operators is given by, so ut is the unitary operator. It is given by e to the power minus ht, where h is the Hamiltonian, where h is termed as the Hamiltonian. Now since Pauli matrices are unitary, so they can represent quantum gates like x gate for sigma x, y gate for sigma y, and z gate for sigma z. So since these are quantum gates, these quantum gates are reversible and norm preserving, which these two conditions are necessary for quantum gates. So these Pauli matrices can act as the quantum gates because they are reversible and norm preserving. Hence Pauli matrices directly correspond to single qubit gates. Now to maintain unitarity in quantum evolution and quantum logic operations, let us try to understand the time evolution. So if the initial state of the quantum system is given by ket psi 0, so it is, this 0 means the t equal to 0, that's the, let's take it as the initial state. So when ut, that means the operator acts upon the initial state, the resultant quantum state is given by ket psi t. So therefore, if the resultant state is ket psi t, if the Hamiltonian is Hermitian, then the evolution operator must be unitary, because the operator is given by the time evolution is given by e to the power minus ht. H is the Hamiltonian. Now if the Hamiltonian is Hermitian, therefore the time evolution will be unitary. Now this guarantees the norm of the quantum state remains 1. Now we can prove this also if we take the inner product of the resultant quantum state. This we can psi t, inner product of psi t by itself, then we can replace psi t with ut ket psi 0, since the first part is the bra part. So therefore we take the bra of psi 0 and adjoint of the ut operators, and the second part is the ket psi part. So therefore the ut ket psi 0 will come. Now we know that the because since this is unitary, so adjoint u when multiplied by u, so we will get the identity. So therefore it is basically 1. So it is equal to the inner product of ket psi 0 with by itself, so which is equal to 1. Hence the norm is also preserved in the Pauli matrices. So they are perfectly single qubit quantum gates. Now if we take the determinants of the Pauli matrices, if you try to find out the determinant, all the three Pauli matrices will have determinant equal to -1. So all Pauli matrices have same determinant and is equal to -1. The trace of all the Pauli matrices is 0. What is trace? Trace is the sum of the diagonal elements. So when you try to find out the trace of the Pauli matrices, you will see that the trace will be 0. So all Pauli matrices are traceless. But if you try to find out the trace of the identity matrix, it will come out to be 2. 2 cross 2 identity matrix. If you try to find out the eigenvalues and the eigenvectors of the Pauli matrices, then to find out the eigenvalues, let us write the let us try to solve it for sigma 1 first and write the eigenvalue equation. So sigma 1 v is the eigenvector. So lambda, let's take lambda as the eigenvalues. Now if you consider the characteristic equation of sigma 1, which is equal to the determinant sigma 1 minus lambda identity matrix, and we put it equal to 0, we find out that the two eigenvalues which come out to be are +1 and -1. So corresponding to +1 and -1 eigenvalues, we need to find out the eigenvectors. So let's do it for lambda equal to +1. So this is the eigenvalue, which is lambda equal to +1, and we will try to find out the eigenvector corresponding to this eigenvalue. So therefore the if lambda is equal to +1, so we will write the eigenvalue equation as sigma 1 v plus is plus superscript is there for eigenvalue equal to +1. So eigenvalue is 1. So v plus is basically the eigenvector, and if we try to find out the eigenvector, we will see that the eigenvector comes out to be 1 over under root 2 and 1 1. This is a normalized eigenvector we will get. For lambda equal to -1, which is the second eigenvalue equation, which is the second eigenvalue, and using the eigenvalue equation, we can find out the normalized eigenvector for lambda equal to -1 also. And we are representing it by V minus. So this is given by 1 over under root 2 and this column vector. And for the other two Pauli matrices, we can repeat the same procedure and we can find out all the Pauli matrices are having the eigenvalues as +1 and -1, and correspondingly we can find out the eigenvectors for all the three Pauli matrices. Now there is an important operator, which is the commutator relation we have to establish. Now what is commutator? Commutator is represented by commutator between two operators is represented by this square bracket. Let us say there are two operators A and B. The commutator is given by, the commutator between A and B is given by AB minus BA. Now if we try to find out the commutator value in all the three Pauli matrices, let us say first between sigma 1 sigma 2, and it will come out to be 2 iota sigma 3. And if we try to find out sigma 2 sigma 3, it will come out to be 2 iota sigma 1. We can easily prove by putting the values of the Pauli matrices, we can easily prove this value, which is the output, 2 iota sigma 3, 2 iota sigma 1, and for sigma 3 sigma 1 we will get it equal to 2 iota sigma 2. All other commutator pairs will vanish, will be equal to 0. For example, commutator between sigma 1 sigma 1 is 0, sigma 2 is 0, and sigma 3 is 0. We can in general summarize the commutator relations with this general value, which is given by sigma j comma sigma k. So these are the two operators we take. J and k both vary between j and k vary from 1 to 3, and we take another index L to represent this all the commutator values in a general formula. So 2 iota sigma L equal to 1 to 3, L will vary from 1 to 3, and we put epsilon subscript jkl. Now this is known as Levi-Civita symbol. So when Levi-Civita symbol is defined such that when the indices jkl are all different and they appear in the order. For example, they appear in the order 1 2 3, 2 3 1, cyclic order 3 1 2, then it will be equal to 1. So if the anticyclic if it appears in the anticyclic order 1 3 2, 2 1 3, and 3 2 1, it will be equal to -1. All other will vanish. This Levi-Civita values for all other orders will vanish, will be equal to 0. There is another relationship which we need to calculate for the Pauli matrices, which is known as the anti-commutator. So previously was the commutator, now it is the anti-commutator. Now anti-commutator between two operators A and B is represented by these curly brackets, and it is given by AB plus BA. Commutator was AB minus BA, so anti-commutator is AB plus BA. If we try to find out the anti-commutator values between sigma 1, sigma 2, which will be equal to 0. Sigma 2, sigma 3 equal to 0. Sigma 3, sigma 1 will also be equal to 0. But if we try to find out the anti-commutator values between the same operators, like sigma 1, sigma 1, it will be equal to 2 times the identity matrix. And sigma 2, sigma 2, sigma 3, all will come out, the value will come out to be 2 times the identity operator, identity matrix. We can again in general represent this relationship by sigma j and sigma k. So j and k both vary from 1 to 3, and we can represent this general equation as twice of delta jk identity. So delta jk is the Kronecker delta. It is equal to 1 when j is equal to k, otherwise it is equal to 0. So this will take care of the values. Now the basis vectors, we have to see what are the basis vector for the three Pauli matrices. We can use them as the basis vectors. Now if we are using the Pauli Z matrix, the basis vector used previously we have used the basis vectors as ket0, ket1. they basically belong to the poly Z eigenbases. So poly Z, so ket Z plus, which is equal to the ket 0. So this is the plus eigenbasis value, which we call as the ket 0. Basically ket 0 and ket 1 are the eigenbases, are the poly Z eigenbases that we can use for the quantum systems. In the same way, we can have the eigenbases for poly X gate. The value is given by this 1 over under root 2 ket 0 plus minus ket 1, and these are the eigenbases. Similarly, we can use the poly Y eigenbases, and the value is given by this 1 over under root 2 this column vector. So 1 over under root 2 is basically for the normalization condition. Now the next thing is that as I have told you that these Pauli matrices can act as the single qubit quantum gates also, because they maintain the unitarity and the Hermitian property. Now let the sigma 1 or sigma x will result into a poly X gate. So this is the X matrix, and when X matrix X, it takes single, so this gate basically takes single qubit as input and it outputs single qubit. This gate is basically a NOT gate. So when you apply poly X gate on ket 0, the output will be ket 1. So you can prove this also. How you can prove this? This is 0 1 1 0, this is X matrix, this is ket 0. Ket 0, we know that 1 0, if you multiply the two, it will result into ket 1. If we apply poly X gate on ket 1, it will result into ket 0. Now if we apply poly X gate on ket psi, a general quantum state, ket psi is given by alpha ket 0 plus beta ket 1, you will see that the coefficients are actually flipped. So alpha with ket 1 and beta with ket 0. So that's the result of basically NOT gate, which is also known as the bit flip. So poly X gate will actually perform the job of bit flip. Let us look into poly Z gate. So poly Z gate, it is basically the sigma 3 matrix or sigma Z matrix. So it can act as a poly Z gate. So matrix is given by 1 0 0 minus 1. When Z acts on ket 0, it will result into ket 0. So the state remains the same. But when poly Z acts on ket 1, there will be negative sign. Basically, there will be phase flip with this ket 1. So this is known as phase flip. If we apply, if we take the general quantum state or the qubit as alpha ket 0 plus beta ket 1, and we apply the poly Z gate, so you will see that alpha coefficient remains same, but beta coefficient will get the phase flip, because beta coefficient is the coefficient for ket 1, so it will get the phase flip. And for the poly Y gate, so poly Y gate is basically a combination of both bit flip and phase flip. So if you apply poly Y gate on ket psi, so this is poly Y gate and this is our ket psi, and if you calculate this, you will see that the coefficients are reversed. That means alpha and beta are swapped. So that corresponds to bit flip, and beta will get a negative sign. Beta with negative sign is phase flip. So poly Y gate is actually poly Y gate results into a combination of both bit flip and phase flip. So this was all about the Pauli matrices. Thank you.